One of the cool things in math is when you learn how certain people are able to do things so quickly. It's these shortcuts or patterns that they learn about. And so today we're going to talk about something called the binomial theorem, or expansion. And it's based on a pattern. So let's take a look first at x plus y to the 0 power. Anything to the 0 power is
1.
1. That's ridiculous. 1. If I look at x plus y to the first power, that would give me x plus y. If I look at x plus y squared, I get x squared plus 2xy plus y squared. If I look at x plus y cubed, you probably don't know this one. You might. You get x cubed plus 3x squared y plus 3xy squared plus y cubed. Now the interesting thing is, although we don't write them, each of these variables have a leading coefficient. So like what I mean by that is this is really like 1x plus 1y, 1x squared plus 2xy plus 1y squared, 1x cubed plus 3x squared y plus 3xy squared plus 1y cubed. So they don't really write down these coefficients when they're 1. And if you look at Pascal's triangle, this is what Blaise Pascal discovered. He's right up there on the front of my wall. This is Pascal's triangle. Notice, these numbers are the coefficients of the variables. Do you notice that? Kind of weird, huh? So there's a way to find those things in mathematics, those numbers that are these coefficients. And if I were to write in all of them in that same color, you would see Pascal's triangle show up as the coefficients of each of the terms. So that's kind of a cool pattern. That'll be useful for some of the things that we're going to do today. The way that you find this expansion is through the use of a formula down below. It's this formula right here, which has to do with combinations that you learned about in Algebra 2, hopefully. At least I taught it in my Algebra 2 class. And they oftentimes will use a different symbol to mean the same thing, and I'll talk about it in both ways as we do some examples. And on your calculator, you can actually use the combinatorics button or menu item to do this same thing for these coefficients. And I'm going to show you all three pieces as we go along. They're all exactly the same, but just to give you an idea of what's going on, I'll do it while we do it in the context of a problem. In number 1, I'm going to do one example with just straight up algebraic way, and then I'm going to start using the calculator. Okay? So in letter A, the meaning of this stuff in letter A is saying, if you go back to your formula sheet from before, that this thing, the 8 is representing the n, and the 3 is representing the r. So this is really talking to me and saying 8 factorial over 8 minus 3 factorial, 3 factorial. So the top is called n factorial. The bottom is n minus r factorial, r factorial. The 8 and the 3 come from the left and the right sides of that c. And the 5 is the difference between those two numbers. If you remember our pattern from before, we learned that this thing really could be written as 8 times 7 times 6, and I keep on going forever. And what I notice is since I have a 5 factorial on the bottom, I put a 5 factorial and stop, because that means keep on going forever. But down below, I have that 5 factorial, and I also have a 3 factorial. And it doesn't matter if I go 3 times 5 or 5 times 3. Same with factorials, doesn't matter one way or the other. And then, because I see something that's the same on the top and the bottom, those reduce, of course, so those are gone. You might not recall this, but 3 factorial, it means 3 times 2 times 1, which is the same as 6. So those cross off. And my final answer then means that I get 56. So 8C3, which also sometimes is talked about as 8 choose 3, is 56. So now what I'd like you to do is watch as I do this on the calculator, because really this is the way you probably should always do this unless required to use it on a non-calculator part. So put your calculators down, put your pencils down, take a look. 8C3. On my calculator, I will type in an 8, then I will go to math, and then I will go to PRB, which stands for probability. I will arrow down to the NCR, and then I will hit a 3, enter, done. Moving on, from now on, I'm actually only going to type this stuff into my calculator. So what you'll find out is when you type in 8C0 on your calculator, and you punch that in, you will get a 1. In fact, anything C0 will always be 1. Because what ends up happening is you actually have 8 factorial over 0 factorial and 8 factorial. What's 0 factorial? 1. And 8 factorial divided by 8 factorial is also 1. So that's why you always get a 1. 0 factorial is 1. We covered that in the very first section of chapter 9, I believe. 12 and 3 in a parentheses. This is not a fraction. This thing here in letter C is representing the same thing as 12C3. So you can either write it as 12C3, which stands for combinatorics, or you can put it in this parentheses looking thing, top to bottom. It means exactly the same thing. If you type that into your calculator, you find out the answer is 220. Again, I'm not going to spend your time actually demoing this on the calculator. It's 12, math, PRB, NCR, 3, enter, 220. In letter D, I see 6 and then a 1 in this parentheses thing. This again means the same thing as 6C1. If you were to actually write it out, you would see 6 factorial over 1 factorial, 5 factorial. And if you work that out, you find out you get 6. In fact, anything C1 will always be the thing on the left of the C. So if you look to the left of the C and you see something on the right of the C and it's a 1, the answer is always the number on the left. In the next part, it's just a fun fact. 12C3 is the same as 12C9. Why? 12C9 is 12 factorial over 9 factorial, 3 factorial, and 12C3 is 12 factorial over 3 factorial, 9 factorial. The only reason that they're, the reason that they're the same is they have the same denominator, just in different order, and multiplication is commutative, which means you can go 3 times 7, 7 times 3, same answer. Same true for factorials because it's about multiplication. And so the interesting thing is, if it makes your life easier, you could rewrite it as a different combinatorics and get the same answer, is what they're trying to tell you. I'm going to color code how we use this binomial expansion theorem to help us find out how to do the following problem. If you were